first one on that packet, this is, like I said, page 7 of that packet, is asking you to deal with this quadrilateral and to classify it then as, you know, a particular type of quadrilateral if we can. So the first thing we want to do is we want to graph this thing, and I'm going to graph this A as 2, 3. Let me use, I don't know if you guys will be able to see these ordered pairs very easily. 2, 3. B is at, oh, that's terrible. That's negative 2, 3. 2, 3's over here. Sorry. B is at negative 4, 3. So 1, 2, 3, 4, 3. C is at negative 2, 6. So there's 3, 4, 5, 6. And D is at 1, 6. All right, so I know maybe you can't, it's kind of messy, I think. At least looking at my screen, it's messy to see those ordered pairs written in there. But if I go ahead and construct the quadrilateral A, B, C, D, first thing is, does it look like a parallelogram? No. Okay? But remember, we don't want to go off of looks. Okay? Looks can be deceiving, right? Now, generally speaking, in a coordinate plane, because things are to scale in a coordinate plane, as long as we make our x-axes and y-axes kind of increase by the same interval, the argument that it looks like a parallelogram or it doesn't look like a parallelogram should be kind of validated. But what we need to do is still provide math that shows that it is or is not a parallelogram. Okay, so we know, based off what we've been doing for a long time, maybe the best thing to decide whether this thing's a parallelogram or not is to deal with the slopes. Okay, so let's find the slope of C to D. Okay, so slope of C to D. So I'm going to take 6 minus 6, right? Take the y values and subtract them. So 6 minus 6. And then I'll take the x values, negative 2 minus 1. And I get 0 over negative 3, right? So that slope simplifies to 0. Now I'm going to do the same thing with B and A, because they're opposite. And that's what we're usually looking for with parallelograms, opposite sides. So 3 minus 3 again. And then negative 4 minus 2. So in that case, I get 0 over negative 6. So that gives me 0, right? Okay. So at that stage right there, we know that these are parallel. Correct? Now here's my question. There's a lot of other different ways of approaching this, and we'll talk about it. But so far, it's a parallelogram, right? Let's go look at those slopes. Because those slopes provide the components that we need to determine distance, don't they? If I found the distance, using those components for that green segment right there, the distance of that green segment is going to be 3 units, right? Square root of the 0, square root of the negative 3, add them together, and then take square root. Gives me 3, right? That length is 3. The length of the bottom segment, A to B, is going to be 6, isn't it? Okay? So if this was a parallelogram, you would know opposite sides would have to be what? Equal. They have to be congruent, right? Did we just show that they're incongruent? We showed one was 3 and one was 6, right? Incongruent means that they're not congruent. Okay? So that's actually enough to say this is not a parallelogram. Because in all parallelograms, both pairs of opposite sides have to be congruent, right? We just showed one pair of opposite sides not congruent. Okay? And that's nice because in using that information, all we had to do is the slopes. The component for the slopes then provide us the distance. I didn't write the distance down, but we can maybe infer that. Most of you would probably have done this, which is fine. Find a slope of BC. So I get 6 minus 3. And then negative 2 minus negative 4. So I get 3 over, now negative 2 minus negative 4 is what? 2. Okay. I'm getting a lot of people to struggle with a negative number minus a negative. Okay, so just be careful with that. That becomes a positive, right? The negative 2 plus 4. And I think if you write things down, you're less likely to make that mistake. And then I want to find the slope of dA. And so we go 6 minus 3. And then I'll go 1 minus 2. So I get 3 over negative 1, which is negative 3. Are those two slopes the same?
No.
No. Okay. So that tells me that that line right there and that line right there are not parallel, right? So this thing is not a parallelogram, right? Okay, well, that's the thing. If it's not a parallelogram, remember, back to the flow chart that we talked about earlier, we had, what, polygons here. In polygons, we had a subgroup of quadrilaterals, right? That subgroup of quadrilaterals went down to parallelograms, and that went off to rhombuses, rectangles, right? And eventually those two things come together and provide us the square idea, right? But we just said it's not a parallelogram. So if it's not a parallelogram, it's not one of those, is there any way it could be that? Is there any way it could be that? Is there any way it could be that? Right? Because those are all subgroups of parallelograms, right? So what's it default back up to? Quadrilateral. Okay? And right now, that's the only thing that we can classify it as, because we have not talked about the other types of quadrilaterals, which are kites and trapezoids. Okay. Now, from what you know in previous courses, what does that thing look like? Trapezoid. Okay. And we'll talk about the definition of a trapezoid tomorrow, but it's simply one pair of parallel sides. Okay. Quadrilateral with one pair of parallel sides. And that's what we've shown here. We've got one pair of parallel sides, the ones that have slope 0. That defines that thing as a trapezoid. Is that doable? Okay. So because we don't know this stuff in red, we would just classify it as a quadrilateral. Okay, based off of what we have addressed and talked about. Same thing happens on this one here. That one is not, you're going to deal with slopes maybe, find out essentially all the slopes are different, therefore it cannot be a parallelogram. And we'll talk tomorrow how that one actually gets classified as a kite. Okay? All right, so I want to get down to this one. This one I think is one that people struggle with a lot, but there's a lot of good stuff inside this question in regards to where we're going in this chapter and in the next couple sections, and where that takes us maybe in a physics course, or maybe it takes us in a college algebra or trigonometry course, or how we'll maybe use this every single day in a calculus course. And it's analytical geometry. It's basically saying, if I want to show that the diagonals of a parallelogram bisect each other, okay, and I want to show that that happens all the time in every single parallelogram, the idea is that I would have to take every single parallelogram that ever existed. So that's a lot, right? That's an infinite number of parallelograms. And I would have to make sure, I have to go through every single one of them and see that the diagonals bisect each other, or essentially show that the diagonals have the exact same midpoints, right? Is that going to be possible? Can I ever show something infinite number of times? No, I can't go, because I'm going to run out of time, right? I'm going to die doing that. Somebody's going to pick up my pencil and continue the task, and they're going to die. And then everybody in the world would follow suit. They all die before they can show all the infinite number of parallelograms in which diagonals bisect each other, right? So what we want to do is we want to say, okay, if we can't do it that way, if we can't show the specific situations, the infinite number of specific situations, can we choose arbitrary values and see if we can come up with a relationship with these arbitrary values? Meaning that if we choose A, B, and C as being arbitrary values, meaning they can be anything they want to be, they're variables. Does that make sense? And I can show a relationship with those arbitrary values. So if they're anything that they want to be, that will be enough to show the infinite number of situations being true. Okay? So kind of keep that in mind as we go through this process and you start seeing the information that we gain from this process. Hopefully it opens your eyes to seeing that we're essentially showing the infinite number of situations. Okay? And that's really a key component to understanding where a lot of our theorems and proofs and formulas really come from. Okay? It's not good enough to just take a handful of specific situations, show, well, it's true for these 3 or 4 or 5 things, so I'm going to make the argument that it's true for all things. Well, that's not enough. Okay? So we need what we call a general situation. This is a general situation for a parallelogram. So what we want to do is take this image and see if we can put it in the coordinate plane. All right, so they tell me that K is located at 0, 0. A, now I don't really like how they use capital A here and then they use lowercase here as one of the coordinates. But capital A, the point A, is located at lowercase a, comma 0. And remember, lowercase a is just some number, right? So all I'm going to do is I'm going to travel from K, some distance A, and then once I get there, I'm going to go some distance in the y direction of 0. Well, doesn't that mean A, that point, has to be located right there? Now, you could have, like I said, you could have moved it, you could put that point really anywhere you want to, but what we're arguing then is that the distance between K and point A is that lowercase distance A. Does that make sense, everybody? So, this length here, all these braces, that length A is what we're talking about, okay? Could be 3 units, could be 5 units. For instance, if A was 5, wouldn't that distance from K to A be 5? Is everybody all right with that? Okay. Now, the one thing that we could talk about, I'm not going to, but they don't give us any, now, because there's no symbol here, there's no sign, most people are going to think, well, it's got to be positive then. Well, what if I said A was -3? It'd be over here, right? Does that make sense? So A could be a negative number, all right? But we just like to, a lot of times the things that we're going to do right now, we're going to just try to force these, if they have positive symbols or signs, we're going to just let them be positive in the way we think about it, okay? The next thing we want to do is plot I. Okay, so I is A plus B, comma C. Okay, well, A plus B, comma C. If I'm at 0, 0, and I want to go a length of A plus B, then I need to go out this length of A, right? And then maybe some smaller distance, or it doesn't have to be small, it could be a larger distance. Just for my drawing sakes here, I'm going to make it a smaller distance. Let's say that's B. So if I go A, and add to it this blue B, do you see that you would be at an X value right here, right now, right? Now it says, so that's where your X coordinate would be for I. Now we want our Y coordinate to be C. Well, we haven't defined what C is anywhere, so let's just say that C is maybe up here. Okay, so that distance on the y-axis is C. Is that okay with everybody? So you see that if I started at 0, 0, and I travel A plus B on the x-axis, and then a distance of C on the y-axis, I would be located or positioned at A plus B, comma C in the coordinate plane. Is that doable? Okay. Now, the last ordered pair is T, and it's located at B, comma C. Well, if it's located at B, comma C, let's actually look at the C value first. Because it's the same y coordinate as that point, do we agree that this point T has to show up on that line somewhere? Does that make sense to everybody? But now where does it show up? Would you guys agree that that B length, though it was B here, let me actually group that so it'll be easy. It's B here, but is it still B here? There's still a length of B there. So the length of B there, is that going to make sense? The best place would be to think about B being there, right? If I go over, so from this point is located at B comma C, start at 0, 0, go over B, and then up C. Does it make sense that my point should be right there for T? Okay. So we'll just do it this way. We'll clone that distance. That distance B is placed there. And now I have T located at B comma C, where that vertical distance C is the same as the vertical distance of C over here. So now we've got, I'm going to get rid of this line. Now we've got that set of vertices to where if I connect them, K to A to I to T, and then T back to K, you get that shape, right? Now, I'm just going to clean things up a little bit, get rid of some of this stuff. The question is, use coordinate geometry to prove that this thing's a parallelogram. Okay? We've got a couple options. I'm going to go through two of them. First one, most people probably use slopes, right? Can we find the slope of IT? The slope of IT. You would take your y values of I and t and subtract them, right? So the y value of I is c. The y value of t is c. So I go c minus c. And then you take the x values of I and t and subtract those. So the x value of I is a plus b. You're going to subtract the x value of t. Now you're going to evaluate that. You're going to simplify. What's c minus c? 0, right? What's a plus b minus b? Just a, right? Okay. Now we know regardless. So I'm going to show you this in a little bit. Maybe a is 5, maybe a is 10, maybe a is 1,000. It doesn't matter. What's 0 divided by any number a? 0. So regardless of what a, b, and c are, okay, whatever I choose, that slope of that horizontal line IT will always 100% of the time be 0. Okay. Now I want to find the slope of KA. So slope of KA, because I'm looking for a parallelogram here, right? So I'm looking for opposite slopes, or opposite sides in their slopes. So now let's take my y values and subtract those. So 0 minus 0 just gives me 0, right? And I'll go a minus 0. And that again gives me 0 over a, right? Are you seeing that those two things are the same? Regardless of what you chose for a, those two things are going to be parallel. Okay? Kind of show you a visual of this. I've taken a GeoGebra and kind of worked this out where this is point A plus B comma C, and this is B comma C. And let me actually write this way, capital A. I kept misspeaking last class with the labels of these things, so. All right. So obviously we know it's the horizontal line, right? Okay. And if I click slope, it tells me my slope is 0. But what the computer is doing right now to figure out the slope is it's simply taking this c value minus that c value. So it's taking 12 minus 12, right? Okay. But this applet shows me it doesn't matter what c is. Maybe c is 1. So I get that parallelogram. Is that slope still 0 right here? Maybe c is 41. I get that parallelogram, right? Is the slope still 0? Maybe the slope is, I don't know if this will work, let's say pi. Okay? So my C value is 3.14. It's an irrational number. It goes on forever. But is the slope still 0? Because it's taking pi minus pi, right? You see how it's putting in those ordered pairs right there when I put my cursor on top of it? 17 comma pi. Well, where does that 17 come from? It's the A plus the B, right? It's those two numbers being added together. Okay? So what I wanted to show you there is that regardless of what you chose for C, A, and B, when you do the slope, this line is always going to be horizontal, and the slope's always going to be 0. Same thing for K to A. All right? Now let's do these slopes. Let's do the slope of, let's do KT first. Slope of KT. So I'm going to take my Y values, subtract those. So C minus 0, C minus that 0. And then I'm going to do on the bottom my X values, B minus 0. So that just gives me C over B, right? So the slope is C over B. What's nice about that, think about this. I now know if I put this point here, T, at, let's say, 2 comma 5, the slope of that line is going to be 5 over 2. I just take the C value and I divide it by the B value. Does that make sense? And then it allows me to change that. Okay, what if that B value was 3 and the C value was 12? I would have 12 over 3. Okay? So C over B is that slope. Let's do IA. Slope of I to A. Take your Y values, subtract those, C minus 0. And now take your X values, A plus B minus an A. Numerator gives me just C, right? What's the denominator give me? B, right? A minus A is 0. Okay, so 0 plus B is just B. What did we just figure out about those two slopes? Yeah, they're the same. So those two lines are parallel, right? Okay, and the slope of this line is dictated by that point right there. Okay. Now, if I come over here to the GeoGebra that we've created here, and I just put out, let's see here, let's say I take C over B, right? C over B is equal to that number J. So I'm just going to write that, so it puts that number right here. So that's the slope right here of that point. So let's go back to, or that segment. Let's go back to saying this is maybe 4. Let's do some things that are easy to divide, common factors. If I look at this slope right here of that line, you see it's 1, right? Well, where does that 1 come from? It's the B divided by C, right? Okay, if I divide those, that's that number right there. That's the GeoGebra's doing that calculation. Well, what if C was 8? 8 divided by 4 is now 2. And you're seeing that GeoGebra is going through a different way. The reason I put the slope in here is because GeoGebra is actually going through the slope formula to do that, right? It's doing y2 minus y1 over x2 minus x1. But to get this 2, it's just dividing these two components. Okay, so it's giving you two different calculations, but providing the same result, right? I can make these things anything I want to. 14 and 8. Okay, so you get 0.57. Well, 4/7. If you divide that, you get 0.57. Okay, these two things divide to give me 4/7, don't they? 2 divides into both those. Okay, so I think that's kind of important to kind of be able to attach this general situation, okay? Because this is the general situation. Does that make sense? And when I start to input these values, these are specific situations. But we're seeing the results of these specific situations to resemble the general situation, right? But my hopes are that you understand that there's an infinite number of these parallelograms we could create. Okay, we could, let me actually show these things real quick, because these are the sliders that these things are attached to. I could change this A value, and you see, and it's actually going really fast there. Let's go back to increments of, let's go by 1. Man, All right. You see all these different parallelograms that I could create, right? And you can hopefully visualize that even just by changing the A value, there's an infinite number of that parallelogram that I'm going to get through, right? Well, it would be impossible for us to talk about, that one and say, okay, do all these slopes, are opposite slopes the same? And then say, okay, well, now I want to talk about that one. And then I want to talk about that one and do those calculations and verify that, yes, in every one of those situations, opposite slopes are the same. So we do it with this general situation. Regardless of what these values are, we do see that they're going to be the same. Does that kind of make sense? Okay. Now, there's other ways of doing this, and this is, I think, another unique, I think, beneficial way of discussing this question. If we talk about, in this point here I erased was I, A plus B comma C. Let's talk about the diagonals here. Can we find the midpoint of that diagonal? Remember the midpoint, so the midpoint of Ki. Remember you find that by taking the x values and adding together and divide by 2, right? So if I add those x values, if I add that x value and that x value, you just get A plus B, right? And if I divide that by 2, I get A plus B over 2. Is that okay with everybody? Now we do the same thing for my y's. So I'll take that y value and that y value, add them together. So what's that give you? C. I'm going to divide that by 2. And there's my midpoint of that diagonal. Okay? Now let's find the midpoint of that diagonal. So the midpoint of TA. Add your x1 and x2 together. What do you get when you add those two things together? A plus B, right? And you're going to divide that by 2, correct? What do you get when you add your y values together? C. You can divide that by 2, right? What do you recognize about those two midpoints? They're exactly the same, aren't they? And haven't we talked about through the past that when the midpoints are identical, you have a parallelogram? And that's showing you, regardless of what parallelogram you have, regardless of where the vertices exist in the coordinate plane, you're going to get, when you do the midpoint formula, you're going to get expressions for your midpoints, x's and y's, to be identical. So, looking over here, just kind of relating this back to a picture again, and maybe a general solution, or not a specific solution. If I think about that midpoint, so we said a midpoint was located at A plus B divided by 2. Okay, so what GeoGebra is going to do is going to take this A value that I have and that B value and divide it by 2. So in this case, it should give me, what, 8? Add those two together and divide by 2. And then we're at comma C divided by 2. So now it's going to give me that point 4 divided by 2, so it gives me 2. So I should plot a point at 8 comma 2. And you're seeing that point B right there, right? Okay. Would you guys agree if, I don't know if we need to do this, but if I were to draw that diagonal in, does B look like the midpoint? And here, does B look like the midpoint of that diagonal? We agree with that? And we can go through, and I know we don't like to go off looks, but we go through and we can prove it using GeoGebra's other tools. But now what's nice is, C becomes 12. That thing is still the midpoint of both those, and the diagonals are still bisecting each other, right? If B becomes, maybe that one goes to pi. Okay? Or maybe it goes to some other number, E. Okay? We still get that point B to be that midpoint. All right? And we're seeing that that's the midpoint of both diagonals. Is that okay with everybody? So what we've done is we've gone through algebra there. Get back to the right apple. We've gone through the algebra there to show a general solution so that we don't have to go through every single specific example to prove something. Okay, because that's impossible. All right. A lot of times to prove things, we've talked about this many times. To prove something, you got to show that in every infinite case it's true. To disprove something, you just got to show that in one situation it's false, right? It's really easy to prove something false in comparison to proving something true. In regards to proving things true, we have to generally, most of the time, do something like this with arbitrary values. Okay? Let's talk a little bit. We're going to kind of run out of time here, but talk about these questions from Friday's assignment. Okay? Friday's assignment, this is question 13, says to find the midpoint of AC. Okay? Now you could draw your picture here, and I made the coordinates in these two questions pretty small to where you could draw the picture easily on a graph paper or whatever, or maybe construct your own picture on your own graph paper. But we should be able to maybe do this without a picture if you need to, if you want to. If I look at the midpoint of AC, that means I have to use AC as my endpoints, right? Well, midpoints are add the x's divided by 2. Add the y's divided by 2. So if I add these x's, what do I get? -1, right? And then divide by 2. If I add the y's, I get 3, and then divide by 2, right? Okay. The next part says, what's the midpoint of BD? So BD are the ones that I have circled up there. So if add the x's there, what do you get? -1 divided by 2. And then add the y's, you get 3 divided by 2. So the relationship is what we just talked about. Those two things are the same midpoint, right? So the diagonals do what? Bisect each other. So the shape is a parallelogram. Okay. Now, it could end up being a rhombus. It could be a rectangle. It could be a square. It is a quadrilateral, right? But the best answer is the parallelogram, right? Because it's better than being a quadrilateral. We know more about it, so we shouldn't really call it a quadrilateral if we know more about it. But we don't know enough to classify it as a square, rectangle, or rhombus yet. Okay, and that's kind of what some of these questions later on throughout the assignment are getting at, is do you know enough to make other arguments? And if you wanted to make some other argument, what would you need to know? So if I get down here, it says based on the calculation, based on knowing it's a parallelogram, what can we argue now? What do we know? Do we know both pairs of opposite sides are parallel? Do we know this one? Yep, it's parallelogram, right? That's the definition of a parallelogram. Are consecutive angles supplementary in a parallelogram? Yep. Are diagonals congruent in a general parallelogram? We do not know. Okay, we don't know enough about this shape to say this. So don't check that one. Don't check that one. Are diagonals perpendicular in every single parallelogram? Nope. Are diagonals bisecting opposite angles in every single parallelogram? Nope. Only do that in squares and rhombuses, right? Do both pairs of opposite sides, are they congruent in every parallelogram? Yep. Hopefully we didn't click F. Opposite angles congruent? Yep. Are consecutive sides congruent? No. Okay. So of the objects that I wrote down, those are the only ones you would check off, right? Okay. Now, maybe we can start checking more of those off the more information we learn about that shape. Go through, find distances, go find some other stuff. Maybe we can start highlighting more properties, okay? But off of what we calculated, that's all we can make about that, only arguments we can make about that shape. 14 was similar, but 14, you're going to find out that these two ordered pairs were different, right? So if they're different, can't be a parallelogram, correct? Okay. So we would just say it's quadrilateral, and then we come down here and check this option here that says this shape has none of these properties that you've listed. Okay. Going to $15. Actually, let's go. Yeah, we'll do 15. This is something. If we look at 15 and we look at 16, you see 16's ordered pairs were kind of crappy to have to plot, right? My suggestion to you is that when you're plotting stuff, because our graph is just a tool for us to organize our information. So it doesn't have to be a really great picture. And generally speaking, a lot of times when you're doing this stuff, It doesn't have to be to scale. You're just going to want to say, okay, if I'm going to plot negative 6, 6, that thing better be in this quadrant, right? So maybe I just arbitrarily choose negative 6, 6 to go right there. Now, would you agree that negative 2, 4 has got to be in the same quadrant, but it's not as far left and it's not as far up? So maybe I put B as negative 2, 4. And now C is at negative 4, negative 4. So negative 4 should be between these two, right? But now negative 4 is going to be maybe down here. And because I let that be 4 positive, right? Should be a similar distance going down, right? Does that kind of make sense to everybody? And then negative 8, negative 2. Well, negative 8 is further to the left than all of these, right? So negative 8 maybe over here, and then negative 2 maybe about right there. So you can kind of guesstimate the location of your ordered pairs, which I think is a good idea because it's going to be time-consuming to really draw something to scale, especially if the numbers are really big. Just make sure that when you choose negative 8, that you put it further to the left than negative 6, negative 2, or negative 4, right? When I put negative 4 as my y value, I got to make sure that that's in the bottom 2 quadrants. Okay? Just make sure things respective to one another are located correctly. But now it just says what's the slope of AB. So if I want to find the slope of that segment right there, 6 minus 4 gives me 2, right? And then negative 6 minus negative 2, negative 6 minus negative 2 gives me negative 4, right? So this thing reduces to negative 1/2, and that's what we're looking for. Okay. Now I'll find the slope of DC. So slope of DC is negative 2 minus negative 4 on top, and then negative 8 minus negative 4 on the bottom. Sorry that overlapped. Negative 8 minus negative 4. So what's negative 2 plus 4? 2. What's negative 8 plus 4? Negative 4. So what do we now learn about those two? They're parallel, right? Now, my picture doesn't look like they're parallel, right? They look like they might converge, but we didn't take a whole lot of time to make this to scale. Now it says, what's the distance of AB? When I find the distance, and I'm going to use the slope tool to help us find the distance. You remember doing this. We want to do it with the unreduced version, okay? Because that tells me the exact x2 minus x1 and the y2 minus y1. So that numerator of 2 there, that's your y2 minus y1. So in the distance formula, we square that, right? So give me 4. That is the x2 minus x1. And we square that, right? So it gives me 16. We add those together, put them on the radical. So what's that give me? Radical 20, right? And that will actually reduce to 2 radical 5 eventually, but I didn't ask you to do that. But radical 20 is what you need to put right here. That's the distance. Okay? If I go through and find the same thing with DC, well, I'm looking at that value now, because those were the components of DC slope, right? Is it still 2 getting squared and still 4 getting squared? So is there any way that I'm ever going to get something different than root 20 for that? Does that make sense, everybody? So we have shown that that side, that dotted line, is parallel to that dotted line, but we've also shown that they're congruent. Did I use anything about those two lines? No. Okay. So we have shown that this thing is indeed a parallelogram. But why is it a parallelogram? Because down here you have shown that one pair of sides of quadrilateral to be both parallel and congruent. Those are the boxes you need to check off. Moving onward then, we should be able to check off the correct properties for this thing. Consecutive angles, supplementary, yep. Opposite angles, congruent, yep. Consecutive sides are congruent, don't know. Diagonals bisect opposite angles, don't know. Diagonals congruent, we don't know. Both pairs of opposite sides are congruent, yep. Diagonals perpendicular, don't know. Both pairs of opposite sides are parallel, yep. 4 right angles, don't know, okay. Based off the calculations that we did. If you're going to, this is something to be cautious of. If you are going to use the slope to find your distance, you always want to do the unreduced version. Because if I did this version, that's the reverse, or the reduced version, right? What's negative 1 squared? 1, right? What's 2 squared? 4, right? And I'll put that underneath the square root, I get root 5, correct? Do you see how that is not the same as that 2 radical 5? It's half of it, right? And it's half of it because what number did you divide out of here to get to this negative 1/2? You divided out of 2, right? Okay, so that's why that factor of 2 out of this one compared to radical 5 is missing. Okay, you would still, if you did this, you would still find that to be root 5 and that to be root 5. So you can still make the argument that they're the same, but you don't have the accurate distance. Okay, so just be careful that using unreduced slopes to find distance. Running out of time, so I'm not going to go with anything else on this. But in the other classes, class or 6th period, 7th period, I will go through. I'll start with like 16 and 17. So get those on film, and I'll post all these together. So, and I'll make them aware that they need to go watch the 14, 15 ones as I do 16, 17 with them. So I'll put it all together, and you guys can go back and look at all those. It's very, very important that you heed the warning that this chapter test is going to be difficult. Okay, especially actually it's going to be easy. It's going to be easy given that you know your properties, Gage. If you don't know your properties, it's going to be very hard. You're not going to be able to navigate much of anything if you don't know your properties. Okay, been talking. This is going on like the 5th week of this chapter. Okay, now I know there's a week in there of us not being here, right? Most of us not being here, but we've been dealing with these properties for a long time. Okay, if you don't know them yet, you have to do something. You have to go make flashcards. You have to make a quiz. You have to do something to help you convince yourself of these properties and which properties exist for which shapes, or you are going to struggle mightily on that test. Okay, the feeling in the past is the chapter 5 test was hard. You guys remember that before Christmas. Chapter 6 test, generally speaking, people say it's harder, and it's simply because they don't know their properties. Okay, I know some of you are going to ace it, you're going to breeze through it in half hour. Some of you are going to take a lot of time and maybe not get done because you don't know your properties. So you're sitting and you're thinking and you're thinking and you're thinking. Go through your properties and please learn them. Okay, everybody understand that? All right, get out here. See you. Have a good day.